In today's video, we're going to be talking about different types of vocabulary we use to describe some different types of cells that we'll encounter in Unit 9, and also some vocabulary that we're going to use to describe cells.
Professor Lane will take you to school. AP Chem is Kenny Cool.
Okay, first let's look at what spontaneous means in terms of redox reactions and also in cells. So firstly, we're going to have a positive E cell, which means that we're going to generate voltage. Since our E cell is given in volts, that means we're going to have volts in our product, and we are going to use it to generate some power. Secondly, spontaneous reactions occur in galvanic, or also called voltaic cells. Remember, that's where there's two separate compartments where reactions are taking place. One is reduction, and one is oxidation. The anode is oxidation, and the cathode is reduction. Remember, we have a salt bridge to facilitate the movement of electrons, and in both cases, we have electrons flowing from the anode to the cathode because electrons are coming off at the oxidation and joining in the reduction compartment. This is a new symbol that we haven't seen yet, but it's a delta G. So spontaneous cells will always have a negative delta G. This is called Gibbs free energy, and this Greek letter delta means change in. I'm sure we've seen that before. So this is essentially our change in free energy, which means our products are going to have less free energy than reactants. And this also means that a negative delta G indicates that the reaction proceeds on its own, which is how we define spontaneity. A reaction can still proceed super slowly, but still be spontaneous, which we'll look at more when we get to thermodynamics. But this reaction is overall thermodynamically favorable. Okay, now we looked at spontaneous cells, so let's look at some non-spontaneous electrical cells. So this is going to have a negative E cell, which means we need to put in some voltage to allow us to run. So when we have a negative E cell, that just means how many volts we need to begin the reaction. These occur in electrolytic cells. So remember, that's one compartment. The anode and the cathode are together in a solution, usually a molten salt or another aqueous solution. There's no salt bridge in an electrolytic cell. Conversely, we have a positive delta G, so our Gibbs free energy change is positive, meaning that our products have more free energy than our reactants, and so reaction requires an input of energy. So like we see with our voltage, we need to put in some energy to allow it to run. Also, this is called an endergonic reaction, whereas our negative delta G is called a exergonic reaction. And lastly, that means that this reaction is thermodynamically unfavorable, which is how we describe non-spontaneous redox reactions. Okay, so mathematically, we have a few different ways that we're going to describe delta G, and these first two, just for reference, I want to put them up there. Not that we'll know what these mean yet, but our delta G can equal our change in enthalpy, which is delta H, minus our T is temperature, times our delta S, which is our standard change in entropy. This should have a little knot in front of it. Or delta G can equal negative RT, which is our gas constant, times T times the natural log of K, which is our equilibrium constant. Or in this unit, we're going to use delta G equals negative N, which is our moles of electron, times F, which is Faraday's constant we looked at in the last video, or times E, our overall E cell, which is our overall cell potential. So now let's get some practice in with it. Okay, so let's practice with our delta G calculation using the equation we just learned. Here we have two half reactions and our reduction potentials in this table. This is going to be an electrolytic cell. So already we can predict the sign for our delta G. If it's going to be an electrolytic cell, we know that this is going to have a positive delta G because we have a negative overall E cell in an electrolytic cell, but we're still going to calculate it anyways because we need an exact answer. So we know that what's going to get oxidized is our most positive reduction value in our electrolytic cell, because it's going to take the most to induce that oxidation. It's going to take the most voltage because these are reduction potentials. So it's going to be either the most positive reduction potential or the least negative oxidation potential. So we know that this is at the anode. Oops. And we know that this is at the cathode. So then we know that this is going to get oxidized and this is getting reduced. And so knowing that, these are reduction potentials in this table right here. So what we're going to have to do is flip the sign on this, and then I wrote the overall reaction just to save time, but we would have to also flip this half reaction at the anode, which is why we have water in our product on that side, but water in the reactant on this side. So then if we're going to calculate our overall E cell, we are going to say our E cell equals our E cathode minus our E anode. And so at the cathode, we're going to have 0.34, so say 0.34 volts, don't forget your units, and then we're going to subtract our anode, which is 1.23 volts, and that will... Okay, sorry, I forgot my calculator in the last step, but we should get an overall E cell of negative 0.89 volts overall, which, since we have a negative E cell, that should make sense to us because it's an electrolytic cell. So now we are going to calculate delta G overall for this reaction. So we know from the last part that our delta G equals our negative moles of electron times our Faraday's constant times our E cell potential. So now we can just fill in what we know. We know our moles of electron in this problem is going to be 4, because we would have to multiply this half reaction by 2. Overall, we can see that this gets doubled because at first we have 1 copper solid and then we have 2 copper solids. So we're going to have 4 electrons in this. So we're going to say negative, and I would use parentheses here just so because the sign really does matter here. Then our Faraday's constant is 96,500, and then we're going to say our E cell, which is negative 0.89. This is in volts. And so then we are going to multiply negative 4 times 96,500 times negative 0.89. Then we get a really big number. Remember, this isn't, so this volts is really joules. But remember, so delta G is calculated in kilojoules per mole. So we have our mole of electrons here. So our mole is still going to be the same. But since this is 1.23 joules, we're really going to say this is 123, so 0.00123 kilojoules. So we move 3 to the left, which means we're going to have to divide this big number by 1,000. And then so we should get a positive 343.54 kilojoules per mole. And that is our overall delta G. If you enjoyed this video and how to calculate delta G, as much as I do, definitely leave a like, subscribe, comment, share, and I will catch you guys in the next one. Good luck.